Let's start in talking about section 1.1 in our book, which we are calling inductive and deductive reasoning. Of course, we will have to define those terms so we know just what we're talking about. But if we take a look at the definition of inductive reasoning, it might help us kind of guess what deductive reasoning would be, and we can solve problems using these. Inductive reasoning is the process of arriving at a general conclusion based on observations of specific examples. And this is the kind of thing we do all the time. You will regularly approach something new that you haven't seen before and watch what's happening and make decisions about your own behavior based on what you see. For example, your first time going into a new branch office of a bank might involve you walking in the door and taking a quick look around. You might see people in cubicles talking together. You may see people behind desks with partitions between the people, but an opening in front of them. You may see a line of people in the bank, all kind of looking towards those people who are behind the desk with the partitions separating them. And you might think, well, I know I need something from a teller. And my experience has taught me that a bank teller is often behind a desk with a partition separating the tellers, probably for privacy, but we never really worry too much about that. And then if there's this line of people, you would probably make the assumption that that line of people was waiting to talk to the next available teller. And so you would probably get in line behind the other people. You may ask the last person in line if they are waiting also to see the teller, just to be sure you're in the right spot. But again, we've got some experience and we would know probably what is going on because we know the kinds of things that happen at a bank. And so you would use inductive reasoning, coming up with a general conclusion that this line of people is waiting to talk to people behind the desks, which we call tellers, by noting that, oh, these people are lined up this way, facing that direction. Those people behind the desks are facing towards us. This is what I want to happen. So you notice those very specific examples of where people are and come up with the general conclusion that, oh, I need to wait in a line to talk to somebody at the teller. That's an example of inductive reasoning. And we'll come back to some more examples in a minute. But before I do, I want to talk just a little bit about counterexamples because it's important that we note counterexamples as well. A counterexample is an example that proves your assumption to be false. So it's a conjecture. No, your conjecture is your guess. I apologize. The conjecture is so the counterexample is a proof that the conjecture is false. Conjecture or assumption. Conjecture is often based on observation, so it's more than an assumption. And we may have some very specific examples that would lead us to have a particular conjecture. For example, if I take the number 47 and I add it to the number 73, well, we would add the numbers in the ones place. 7 plus 3 is 10. So I'd put the 0 down and carry the 1 because the 1 is in the tens place. 7 plus 4 is 11, plus 1 is 120, or 12, I apologize, for a total of 120. If I take another two numbers, 56 and 46, and I add those together, 6 plus 6 is 12, write the 2, carry the 1. 5 and 4 are 9, plus 1 is 10. So we get 102. So our conjecture may be that adding two two-digit numbers together we call each of those individual numbers digits. I didn't want to plural that. No, adding two two-digit numbers together gives a three-digit number. We have two examples right there on the screen to prove that that is true. Is it always true, though? I can come up with a lot of two-digit numbers and add them together and come up with a three-digit number. So a counterexample would be a time when I can come up with two two-digit numbers whose sum is not a three-digit number. For example, 11 and 22. When I add those together, 2 plus 1 is 3, and 2 plus 1 is still 3. I got a two-digit number. So that's a very good counterexample, proving that this conjecture is false. And this is important because if you can come up with one example that proves the conjecture is false, then the conjecture is false. And that's something that a lot of people are forgetting. A lot of people are forgetting that that's how science works. If you can come up with one example of when a phrase is not true, then the phrase is not universally true. It may be true in certain circumstances, but you cannot say that is absolutely true. And that becomes important anytime you're evaluating any scientific literature or anything anybody says in the name of science, or anything else for that matter. If you can come up with one counterexample, that means the conjecture is not universally true. Again, may be true in most instances, but it isn't universally true. So we need to be able to find those counterexamples, and you'll be asked to do that in the homework, find some counterexamples. Let's look at some more examples. Let's go back to our inductive reasoning definition and maybe take a couple examples just from using figures. So once again, we're looking for patterns, very specific patterns that will allow us to come to a general conclusion. If I look at that top row of figures, and I kind of ignore the what's going on inside each shape, and I just look at each shape, I can see it goes from a circle to a square to a circle to a square to a, and in your minds, you probably thought circle. So I am thinking the same thing. It's got to be some round shape. Now I see that each of these shapes has an X through it, dividing it into four pieces. So I'm going to keep that because that didn't change. That stayed the same from shape to shape. Now we've got some dots in here, and those dots are changing. If I look at the left figure, I see a blank on top, rotating clockwise. I see 1 dot, 2 dot, 3 dot. If I go to the next figure, now the blank is over to the left and rotating clockwise 1, 2, 3 dots. Next figure, now the blank is on the bottom, rotating clockwise 1, 2, 3 dots. And then the next figure, the blank is on the right, rotating clockwise 1, 2, 3 dots. So it looks like this thing, this set of points is just kind of rotating through those quarters. So we had the blank on top, blank left, bottom, right, should be back on top as we follow the pattern. So if that's on top and we rotate clockwise and get 1 dot, then 2 dots, then 3 dots, Now we have found the next figure in this particular series. Think about those patterns. Notice we started with the general shape, and then we looked at, well, they all have an X, so we put an X in, and then we looked at what's happening to the dots. We can do the same thing with this next one. We've got looking at shapes, square, triangle. You're thinking square, as am I. There's nothing inside those shapes, so we're good with that. We don't need to put anything inside our last shape. That would be weird. Let's look at, well, what's changing is the thing on the bottom. We've got one line on the bottom. They all have dots on them, so we'll just talk about the lines. We've got one line, then two lines, then three lines, then one line, then, well, you're probably thinking two lines, which is what I'm thinking. We'll put the dots on the bottom because they all have them. And that would be our next shape in the series. So notice we're just looking at patterns. What's happening as we move from one symbol to the next? And what would the likely pattern be? Now, it doesn't mean that is the actual pattern. And that's the weird thing. What we're doing is we're making observations and guessing or coming up with a logical conjecture for what the next shape would be. Doesn't have to be, but there's a good chance that it is. That's kind of the way this works, is we look at patterns and we make an educated guess as to what might be next. Let's look at some number patterns. Maybe we've got 3, then 12, then 21, then 30, then 39, and we're asked to find what's next. Well, I like to ask myself, well, what does it take to get from the first number to the second? Well, I could multiply by 4. That would work. Or I could add 9. I'm not going to subtract and I'm not going to divide because the number's getting bigger. So I'll probably multiply or divide. Now from 12 to 21, well, that I have to multiply by, got a calculator here. It's not a nice round number. So I'm thinking multiplication is not what I want, but let's try it. And I just take 21 divided by 12, and it gives me 1.75. So I have to multiply by 1.75 to get to the next one, or add 9. Now to get to the next one, 30 divided by 21 gives me 1.428571429. It's about 1.43. I am going to abandon the multiplication because those numbers are all changing. However, if I add 9, I get the next one. If I add 9, I get the next one. So I probably need to add 9 again and go with the 48. Because notice, multiplying didn't give me the same change every time, but adding did. So that's the one I'm going to go with. Let's try another set. Again, we'll start 3, 12, 48, 192, 768, and then our next number. Now that jumped really fast, didn't it? That's okay. We know it's add 9 or multiply by 4. Now the next pair, if I multiply 12 by 4, I get 48, or I needed to add 36. 48, let's just take that 192, divide by 48, gives me 4, as one might expect. And I would have to add 144 to get there. I'm going to abandon the addition. 768 divided by 192 is 4, as you expected. So let's go ahead and multiply by 4, because that was the same for every step. So 768 times 4 will give me 3072. That is likely the next number in that pattern. Now, I do want to point out that if it grows slowly, as our first one did, it's probably addition that is the pattern. Notice this second one grew quickly. So we could say if it grows quickly, it's probably multiplication. Now, that's not always the case, but I have found on the occasion that I shouldn't talk while I'm writing. I have found this to generally be true, that if it grows quickly, it's probably multiplication. If it grows slowly, it's probably addition. Now, like I say, it's not always true, but let's take a look at what we have here. All right, see if we can find a pattern. 3, I'm going to add 1 here, add 2, add 3, add 4, add 5. Well, I'm guessing I probably need to add 6 and get 24. Multiplying is not going to work too well, I think. This will be multiplying by 1.3, and then multiplying by 1.5, multiplying by, well, there's another 1.5. And then multiplying by, what's 13 divided by 9? 1.4. So you can see while we did have a couple of them that were the same, they weren't all the same. Whereas the addition just followed this nice increase. And I like to do it this way, just kind of writing, preferably in another color, underneath the pairs, what it takes to get to from one to the next. That seems to work pretty well at highlighting what the pattern likely is. Again, not always there, but it could be. Let's do one more. 1, 1, 2, 3, 5, 8, 13, 21, and then a blank. So here we added 0, then we added 1, then we added 1, then we added 2, then we added 3, then we added 5, then we added 8. Oh, look at that. 1, 1, 2, 3, 5, 8, 1, 1, 2, 3, 5, 8. Oh, I'll probably add 13 to the next one and come up with 34. This is actually a famous sequence called a Fibonacci sequence, and it comes about by adding the 2 digits to get the third. So 1 plus 1 is 2. 1 plus 2 is 3. 2 plus 3 is 5. 3 plus 5 is 8. 5 plus 8 is 13, and so on. However, when we wrote out the pattern down below of what we added to one number to get the previous number, we saw our pattern duplicating, and that worked really well. This sequence actually appears in nature a fair bit. If you start in the center of a sunflower, for example, and you count seeds in each ring, it kind of follows this pattern. You get a ring of 1 and then another 1, and then you get 2 around that, and then 3, then 5, then 8. And some seashells grow at that sort of rate as well. It's really interesting how math models the world. And these patterns or sequences can really help us figure out what's going on in the world around us. And I think that that is awesome because I like understanding the world. It makes the world so much more interesting. All right, now I want to skip over and talk about deductive reasoning. As you might expect, it's kind of the opposite. So deductive reasoning is the process of providing or proving a specific conclusion from general statements. And so if you come up with that conclusion and it appears to be proved true by deductive reasoning, we call it a theorem. Now, you may eventually find a counterexample that proves it false. But until you do, you tend to assume that it is valid. So let's think of some examples, and I've got some that I'll show here in a minute, but let's go to the game Scrabble. Scrabble is a game in which you place letter tiles on the board and try to spell words. Now, there are certain rules in the game of Scrabble. There is not a rule that says you can't play the word Texas in this game. There's no rule that says that that's the case. However, you can't play the word Texas in the game Scrabble. Why is that? Now, the word Texas, that's a very specific example, but we do have a couple of rules that if we follow those, now these are general rules. One of those is proper nouns are prohibited. So you can't play a proper noun. Oh, well, see, Texas is a proper noun. Proper nouns are those that start with a capital letter. It's a very specific person, place, or thing. And so, because we have this general rule that proper nouns are prohibited, Texas is a proper noun, therefore you can't play the word Texas. Now, there, like I said, there's no rule that says you can't play Texas. However, you can't because there's a general rule that says you can't play a proper noun. So that's an example of when we might use deductive reasoning. Again, we're going from a general phrase, like proper nouns are prohibited, to the very specific, you can't play the word Texas. That's deductive reasoning. Inductive, we went from very specific examples to come up with a general. Deductive, you start with general statements and work your way down to a specific one. Let's look at a type of problem that might or that does use deductive reasoning, and maybe this will help. So we're given a series of steps we need to do, and they want us to select a number. Then they want us to multiply that number by 6. And then they want us to add 8 to the product, divide that sum by 2, and subtract 4 from the quotient. Now, we used some words up here I want to make sure we talk about. Product, sum, and quotient. Product is the answer to a multiplication problem. Sum is the answer to an addition problem. A quotient is the answer to a division problem. And difference, which isn't mentioned, is the answer to subtraction. So those are some terms that you should know or learn. You don't have to know them before now, but if you do, you're just have a leg up. But I do want you to be aware of those as those words will show up from time to time. So let's go ahead and pick some numbers. They want us to pick at least 4 numbers. We will only do a few of them. Let's pick 2, 4, and 7. So let's see what we do. We take 2 times 6 is 12. 12 plus 8 is 20. 20 divided by 2 is 10. 10 minus 4 is 6. So we started at 2 and got our way to 6. Now let's do the same thing with the 4. 4 times 6 is 24. 24 plus 8 is 32. 32 divided by 2 is 16. 16 minus 4 is 12. Now let's do 7. 7 times 6 is 42. 42 plus 8 is 50. 50 divided by 2 is 25. 25 minus 4 is 21. Now, do we see a pattern here? When I started with 2, I ended with 6. When I started with 4, I ended with 12. When I started with 7, I ended with 21. It looks to me like if I multiply the first number by 3, I'm going to end up with the last number. So that's probably the pattern. If you follow these steps, you will probably end up with 3 times your original number. That's probably what's going to happen. Now let's go ahead and test it. Here in part B, it says use the variable n to represent the original number. And we're going to use that. What's n times 6? Well, we write that as 6n. 6n plus 8. There's no way we can simplify that right away, so we just write it 6n plus 8. Now we need to divide that by 2. So what I want to show you here is a couple of ways that we can divide this by 2. One way is dividing both of them both of the terms in the numerator by 2. Because you have a single term in the denominator, we can do that. So now we could do 6 divided by 2 is 3. Still have that n there. 8 divided by 2 is 4. That's one way we can do it. Or we could factor 2 out of the numerator. And I know you don't have a lot of experience with that, but I'm going to show you what I'm talking about here in a minute. What I've done is I've said, if I divide 6n by 2, then that leaves me 3n. So if I were to maybe multiply the 2 back in, 2 times 3n is 6n, and 2 times 4 is 8. So I've divided both of those by 2. And the reason I did that is because now I have 2 divided by 2, which is 1, and I have 1 times 3n plus 4, which is just 3n plus 4. So that's 2 ways you can divide 6n plus 8 by 2, but we end up with 3n plus 4. And now, go back to our original, we need to subtract 4 from that. 3n plus 4 minus 4. Well, if you add 4 and then take those 4 away, you're back to the original, which would be 3n. So sure enough, our process went from n, whatever number we pick, to 3n, which is 3 times n. It really was just multiplying by 3. So we used a little deductive reasoning. We had this general pattern that was set up for us. We got some specific examples from that pattern, and specifically we went to the let's let n be our number. And by following our pattern, we ended up with 3n. So that was an example of using deductive reasoning to come up with the very specific 3 times whatever number we pick based on these very general statements that were the pattern. And that gets us through that first section, a little inductive, deductive reasoning. Don't forget, you use these all the time. I know I'm applying words to it now, but that doesn't matter. What matters is that you get the sense for looking for patterns, finding ways to use those patterns so that you can come up with good conclusions at the end. It will make your life so much better as you start looking for patterns. And you already do, as I said. It's something we've been doing for years. If you've got questions, let me know.